This is the first session of the launch, so I hope you have some blood, not only digest the food, but rather this material over here. Let me introduce myself. I'm Attila Slovenčák, working for Component Soft. We are an education company, a training company working in widely in Europe, practically. We are working for telcos like Ericsson and the Hungarian Telecom as well to deliver training. So you can find this kind of PDF. I mean the presentation material on this QR code, so feel free to download it. Okay. So this talk is about how to build a reliable and highly available OpenStack. And well, there could have been much more buzzwords inside of the title, but anyway, I plan to do some sort of a bird view of this high availability of the OpenStack infrastructure. So we probably don't really go into the code level, so we don't do any kind of deep dive. So let's start. Okay, very first question, of course. Probably you already know the kind of a pets versus cattle principle. So if we want to define whether it has to be a highly available or reliable OpenStack, we really want to define what kind of virtual machine we have to run. So we can run pets. So like this is a kind of a machine that is the target of a previous physical to virtual migration. That is usually runs as a single instance one. Probably it really like a pet, so it has a loving name. It's quite unique, and in case you have a problem with that, then you just struggle to take care and nurse it back to health. So so anytime when you think of backups, when you think of regular maintenance and something like scheduled maintenance windows, then that's a kind of a thing like a pet. So, and on the other hand, you have a cattle like web servers behind a load balancer, which is just numbered. They are very similar to each other, or almost exactly the same as the other. And if I have a problem with one of them, let me shut it down and start it again. So if in cloud, we rather expect something like a cattle, so cattle style VM, because the guarantee sometimes is not so a big one. So if we have a problem with a compute node, then at least the expense of a reboot is required in order to restart the machine, so we have a kind of a downtime. If I'm proactive enough, of course I can figure out that there is a problem with that VM, because smart monitoring or anything gives me a sign, and I can early on live migrate those VMs from one node to another. But most of the cases there is no guarantee that I will run it 100% of the time, so that's a problem. Of course, the real life is not like black and white, so most of the cases I have machines like pets, which is a kind of a database in my structure. So this is a big single instance one, and of course I have a web front end or a web layer, which is rather like a cattle. So in many cases I have to prepare my OpenStack in order to even run pets, pet-like VMs, and that's practically a problem or something that you have to struggle with. But on the other hand, of course, if we say, okay, we run cattle-like machines, then the reliability is not that important. We can go home because, okay, OpenStack is as good as it, and we don't really have to take care of what happens if one node is going down. Obviously, that's true maybe for one hypervisor, but the whole infrastructure has to be protected, so we have to implement some sort of reliable service for, let's say, API calls and anything like that. And we can have many approaches for that. The first approach is an old school one, so that you have a sort of an active passive failover for the most important services. So who are the most important services over here? First of all, we have the RabbitMQ. So the internal signaling goes through the message queue. And if we have a problem with the message queue, like it's going down, we're going to have something like a fail-safe or a half broken scenario. So some of the calls like Nova list, so any kind of listing operations that requires database only, works nicely. But in case you say, okay, I want to do a Nova, let's say a reboot or a reset or whatever kind of thing, so that requires a communication over RabbitMQ to the given Nova compute instance, that's the point when I have a failure. So RabbitMQ has to be reliable. And on the other hand, we need to have a kind of a reliable failover from one RabbitMQ node to another from the OpenStack service point of view. So for each and every service, we can have something like a list of RabbitMQ nodes. And if the connectivity for the first node is broken, then we have to move for another node. This is done internally by the Python framework, so the combo driver and all these kind of things. And with some bugs inside, so sometimes you have to tune those kind of timers inside, how long you wait, or how long you want to retry reconnecting to the same RabbitMQ node before trying to move away from the other point. So this is one thing that needs a reconfiguration if you are not really having that kind of RabbitMQ configuration from the scratch. Like if you are installing with PackStack doesn't really, this is an RDO automatic installer if someone don't know that. So if you are doing that with PackStack, it doesn't really take care of this high availability, so having multiple controller nodes or something like that, so you have to configure by hand that you want more than one RabbitMQ nodes. The other kind of, let's say, real life experience you might have with RabbitMQ failovers is what you can see, for example, in the log output of Nova API. So for every single controller node you have, or where you run the Nova API, probably you run several instances of it. So you have 8, 16 instances, most probably that much how much core you have. And those RabbitMQ nodes are practically, these Nova APIs are just used in a rollover fashion. So if you have if you shut down RabbitMQ on the first node and there is a failover to the other node, for a long time, for a long period of time, you still see errors like still searching for the next RabbitMQ node and trying to fail over, because if you have 16 API workers, then it takes a long time how the last one is just getting to the point when it receives a request, and that's why he has to move. So that's a little bit misleading. It gives you an impression that this failover doesn't really work correctly, but actually it does. But actually you need all the API nodes to fail over, and that needs some time. Okay, the other thing that has to be protected is a MySQL, obviously. So we need to have a reliable database service that is, well, it can be done by a failover kind, what you can see here. Probably the failover, probably most, you know that InnoDB is practically having a crash recovery procedure, which is taking a smaller time right now than previously, but it still takes a time. So we can have an instant failover from one node to another, but we need to wait for the other node to do the crash recovery, and that's why we're going to have some downtime because of this one. So that's why we rather prefer, as again going to be on the next slide, something like a symmetric replication or synchronous replication stuff, which is called Galera, in order to provide a highly available MySQL. And the third thing is MongoDB, which is only required if you're running Ceilometer. Practically you don't need to have Ceilometer in your OpenStack, and someone doesn't really care. Hopefully MongoDB is running in clusters, so you can run MongoDB as well in a failover fashion, or you can run it as a kind of a cluster. And if you choose to have an active passive, so like doing this kind, running these kind of services by via Peacemaker or this kind of cluster frameworks, and you have to have something like a shared storage, like a shared iSCSI or whatever storage, or you might use DRBB in order to do that. But anyway, that is always a requirement. And in this kind of active-passive, I don't know whether we still have some OpenStacks running in this way, usually has a kind of a floating IP or virtual IP that is the IP of the services, and this virtual IP moves along with the API nodes and all the other nodes, so that's how the service reliability is guaranteed. And that's practically a way you can have an active-active controller stuff. By the way, these kind of slides are from our advanced administration training, so you can meet with these slides there if you attend the training. So practically the thing you can have here is that you have a RabbitMQ cluster that is all over the nodes. If you have a lot of money, probably you have 3 controller nodes. But in case you have just 2 sites, but because of the quorum logic internally, for both Galera and for RabbitMQ, you need to have a third leg of the cluster in order to provide, let's say, odd number of nodes. In this case, you can have a third node, which is a kind of an arbiter. That could be just a small node somewhere. Maybe this is under the desk of the IT guy. Maybe it's inside of a cloud. Maybe it doesn't matter where it is, but it has to be reliable and independent of the first and the second controller. And what is practically good in this one, then it doesn't really have the expense of a third node. So RabbitMQ supports the RAM node, which doesn't really serves or stores local data, so it doesn't really provide durability of the messages. And Galera has this Galera arbitrator daemon, which primarily gives his vote in case of, let's say, a split brain scenario. But the most important part of the Galera stuff that it relays the change set of writes that changes happening on one node and another. So if in case you have, let's say, a 2 data center scenario and the connectivity between the 2 data centers is broken, but the connectivity to the arbiter is still provided, and the arbiter can relay the changes, so your cluster is practically not broken in this case. And for MongoDB, you can have a cluster in the same way. There could be an arbiter kind of node, which doesn't really store data, but rather gives you a vote for that. And there's a point when we can talk about the networking stuff. So we have network 1 and network 2, which is a neutral network node. And on these network nodes, I might be running highly available routers. We're going to have some slides later on about that. But the key idea is that we are talking VRRP between the nodes, between these namespaces using a keep alive, and that provides us some sort of failover service. And the same kind of keep alive is used on the top level load balancer if you apply it, or if you use it as or if you do that with AJ proxy. Many vendors are just rely on AJ proxy actively, but you can have any kind of vendor load balancer product in order to finally get an API call hitting the public interface or hitting the internal URL to end up in one or the other API node on one of the other controllers. Okay, great. So let's go service by service. So let's see what is the problem, what could be the problem for one service or another. So the first thing is Glance. So we couldn't have an easier or more simple service than this one. Practically, Glance is just an API node. If we are talking about Glance v2, so the version 2, all we need is Glance API and nothing else is required. Unfortunately, the older version, so the version 1 of Glance, is still needing the Glance registry, which behaves like a database access node to practically the MySQL server. So any kind of, let's say, updates of a image record has to go through the Glance registry. And the other thing, other kind of exception we have inside of the glance is that usually between the processes of one project, like for example between the processes of Neutron or Nova, all the communication is done through the RabbitMQ, so we use RPC call or RPC cast in order to communicate with the other process. But Glance is an exception here, so we use REST API calls for the Glance registry, which means that I might have to have another kind of entry in the load balancer configuration to have a load balancing for the Glance registry traffic as well. Or I can have the choice to say, okay, I have a Glance registry on each and every compute node, and I'm always making the Glance API to talk to the local Glance registry. And there is also a kind of a problem here. The problem is because of the expiry of the token. So there is something like a 2-year-old bug in Glance that if you have something like a long update of a long upload of an image, because you have a low bandwidth connection or something like that, and so this update takes longer than the token expiration time, which is 1 hour by default. Then at the end, if you have something like a disrupted TCP sessions, or your Glance client crashes, or maybe if you are uploading via the dashboard and the dashboard session is just expires, in that case the Glance API, if this connection is dropped, then he's sending a REST API call to the Glance registry to say, okay, this is the point when you have to mark this Glance image as a failed one, but it will send an expired token, so a Glance registry denies this kind of action just because of that. And that's an issue, because the Glance image is just stored as something like in a saving. It is just kept in a saving state and not flagged as failed. The ultimate solution obviously is to move to Glance v2 when we don't have Glance registry, so we don't have that problem. But actually the Nova project has a session in the summit session in the Austin Summit, or Design Summit session, talking about what can we do in order to finally get rid of the first version of Glance. At least the Nova project is still using the version 1 of Glance as far as I know. Okay. What about the Nova project here? So obviously we spread the Nova to several nodes. So we have some controller node services, let's say, something like the Nova API and the scheduler, and the conductor as well. And we also have, of course, the compute, the hypervisor nodes when we have the Nova compute. The first thing is the Nova conductor, which is something like a single point of failure in the whole story. So the thing is that if you shut down the Nova conductor, which is a database access layer again for all the Nova computes, then all the Nova computes go down as well. Obviously, the easy solution for that to spawn more than one Nova conductors on different services, because that's a kind of a stateless engine. So I can solve that problem easily, but if I have only one instance of that, that's a problem. Obviously, the other kind of issue we have is obviously the compute node issue. So what if the compute node is down? Is it a problem for the VMs? I mean, if the Nova compute process is done, is it a problem for the VMs or not? And the general rule of thumb of OpenStack is that if something is provisioned already, then it's just keep provisioned. So if you already started the VM, if you already configured the networking for that guy, it doesn't matter whether you have a running Nova compute on that hypervisor node or not. Those VMs are happy to run. And so the only thing what you don't have as a thing here is that if you want to change something, if you want to change the security group of the VM, if you want to do some actions with the VM, that's not guaranteed or not granted if you don't have a Nova compute running over there. But still, if you shut down a Nova compute on a hypervisor node, and if you just visit your dashboard and check the hypervisor nodes, you will see after a minute of delay, when the last heartbeat of this Nova compute is just missing, you will see a button say, okay, that's the point to evacuate the VM. But usually you don't have to push that immediately when you see something like that, because first you have to check whether it's really just a problem of the Nova compute process or whether it is a problem of the whole node. Because just the process doesn't really mean you have to evacuate and provide some downtime for your service. Of course, evacuation works in the expense of a reboot in case you have a shared storage. Obviously, if you don't have a shared storage, so the VM disks are not stored reliably in a shared resource, then you have a problem. Because the only way to have an evacuation is a kind of a buy a robot stuff. So you send your operator to the machine, and unplug the disk and plug it into another machine. So that's probably not the best case. So what can OpenStack do for this to solve that kind of problem? So to reliably and also automatically do some sort of a failover for VM. If this is a pet-like VM, so what can we do here? The very first kind of thing what you have is a levered feature that you can provision your glance image with a hardware watchdog option. In order to say the lever to configure a watchdog device as well for the operating system, which means that if there is a kernel crash or there is something that is just making the whole operating system hang, then at least you can make a reset. That's not a complete solution against something like a hardware failure, but at least if you have a kernel bug, that solves partially the problem. The other thing what you have provided here is something like running up once again a pacemaker corresponding type of cluster across the whole OpenStack in order to check reliably whether the compute node is down. Reliably means that if I lose communication with the compute node, I should be sure that this guy is fenced out. So we use the good old method of fencing out like the Stoneit. So many OpenStack downstream vendors are providing a kind of a solution with pacemaker and pacemaker remote in order to build up let's say 100 node OpenStack or rather pacemaker cluster, and in case when you have a problem with one of the nodes, then you start an agent which is practically doing no evacuation to move away all the VMs from this node to another node. So just for reboot time, after reboot time you will have your VMs running on another node. Okay. Cinder. Cinder is a kind of a programmatic stuff from the point of view of reliability or high availability, and that's mainly because the Cinder volume. So the original design of the Cinder volume was that, okay, I'm running LVM, I'm running LVM on a couple of nodes, and each and every node is practically running just one Cinder volume process in order to provision the LVM volumes on that specific node. So if that node is broken, then obviously the Cinder volume is not available there, but we don't expect that volume to do anything with other nodes. So we have a record practically, we have a column in the record of the volume that, great, you have that kind of host, and this host is provisioning that volume for you. And that's a problem if you have something like a shared storage. So if you have Ceph or GLUSTRFS, when you have a distributed solution, you might have, let's say, one Cinder volume that could provision the whole stuff. But what the problem is that if I'm running Cinder volume on controller 1 and running the other one on controller 2, when I'm creating a volume through that machine, then the host name like controller 1 or controller 2 is just recorded, and later on, if the controller 1 is down, with the controller 2 Cinder volume cannot really control that volume anymore. So the kind of a hacking what you can do if you're running some earlier versions of OpenStack, is that you do some arbitrary host name and you configure your Cinder volume with that arbitrary host name. So that host name will be, in the configuration of the Cinder volume, will be the same on all your controller nodes. And after that, you can say, okay, great, I'm running the Cinder volume as one instance, and I'm failing it over to another node in case you have a trouble with that original node. So that is the whole OpenStack stuff can be running just through load balancers and just running just another instance. But this is an exception, so that's why I have to spawn some cluster framework in order to keep Cinder volume alive. And if we can trust the saying, Mike Perez, I don't know whether he is here, so I'm quoting here, he was said just immediately that in Newton we're going to have finally the fix of replacing local host level locks into distributed locks, like using up frameworks like Zookeeper or Consul or something like that. And that provides finally a solution for you to have, let's say, a distributed handling of volumes from many independent Cinder volumes. So this kind of exception of needing a failover framework here is finally released. Okay. Heat. Okay, so what's the problem with heat? Or what is the specialty? Most of the things in heat, I mean, the processes are stateless. So from the point of view of reliability or failover, we don't really have a problem here. Usually the one problem that what the heat has is that it tries to use the public URL all the time. It is somewhat interesting because you think of the internal URL registered into Keystone, that is something that you want to use on something like for an internal call from one OpenStack service to another. But the original or one possible way to deploy heat is to deploy it outside of OpenStack, which means that you have to use the public URL, and that's the default config. So in case you have something like a high security setup, from the networking point of view, so your network team is configuring a quite rigid security, then probably you don't let the heat to reach the public URL of another service like Nova when a heat stack is trying to create a VM or something like that. So that's something like an extra configuration you have to hardwire into the heat config to say that, okay, for every and each other OpenStack service, I want to use the internal URL rather. And the other kind of problem I have, and that's not a high availability problem as well, is this heat API CFN stuff. So what is that? Practically, I'm needing this one because I have some features like the wait condition inside of my heat stack. So I'm making one VM to call or to send a signal to this service in order to say that, okay, this post-installation script is finished, or has finished, so now you can spawn the other services, other parts of your OpenStack or heat stack. And that's something which is a kind of an exception here as well, because I need to have a call for an OpenStack API from internally from a tenant network, and that's something that might not be allowed through your security policy as well. So that's another kind of exception for you, and that's why in some cases, for example, in a private cloud I have a support for, there is a note saying that, okay, you can use heat, but please do not use this kind of wait condition feature because this is not settled down yet. How should we let this kind of calls from a tenant network to a heat API can go? Okay, great. And of course, this kind of heat API CFN process needs to have a load balancer entry as well in order to provide reliability. So that's just an additional load balancer entry after the, let's say, the API node. Okay, Ceilometer. I don't know how much who is using Ceilometer in production right now. Not a big number. So anyway, so the Ceilometer is somewhat extra that it is using MongoDB, not only for meter data, but rather using it for your internal database. So like registering resources and anything else, registering alarms as well. So instead of having a reliable MySQL, I need to have a reliable MongoDB here. And we also need an additional component, which is somewhat the same problem. We had the same problem like Cinder has nowadays, that we need to have something like a distributed locking mechanism in order to let this Ceilometer central agent, which is just doing something like a poll for each and every service for those kind of resources that doesn't really poll themselves through the message queue, or those ones that couldn't really be passively monitored through the message queue. So the thing what we have is that primarily the central agent was running as a single instance service, so the same problem was there with Cinder Volume, but the Ceilometer team implemented this or used this TOS framework in order to provide distributed locking. So now I can start the central agent in a something like a active fashion, so I can run many instances, and those guys are just use this framework. And of course the Redis is practically the default engine or the default key value store behind the whole stuff, which finally lets this kind of distributed log be reliably held. And of course that is just a solution of the problem in one way. It poses another problem, that the Redis has to be running reliably, so I have to do some sort of a Redis cluster or Redis replication across my controller nodes in order to provide reliable storage of the logs. And of course I have to set up something like an AJ proxy entry here in order to let the Redis entries be reliably, let's say, reached over, because the entry inside of the Ceilometer configuration is just providing a single IP and single port, and not, let's say, a list of IPs. So that's about the Ceilometer. And yeah, finally the neutron part. So yeah, we couldn't really have a simple diagram about the neutron project. So you can see that here. So it is massively distributed all over the OpenStack cloud. So we have the Nova server, which is the API node running on the controller, and we can have network nodes, and we can have as well, let's say, an agent on the compute node in order to provision the endpoint of the tunnel or the VXLAN or the local Open vSwitch or whatever you want. And we have problems. The problem is that the network node and the tenant router could be something like a single point of failure, and that it could be solved by highly available, let's say, routers, which means that I'm spawning the same namespace on network 1 and network 2, so 2 network nodes, and I'm starting up a specific tenant network, which is I'm going to have a single tenant network for each tenant, this green one over here. So whenever I'm just running or starting an AJ router, this kind of extra network is automatically provisioned for my tenant. And practically that tenant network is used in order to let a guy to one router and a keep alive daemon on one router to communicate with the keep alive daemon on another router. So that's a way to have an active passive use case of routers. So all the IPs, so the IPs of the router itself, and also all the floating IPs are provisioned on one node, on one namespace only, and in case you have an error, then you are failing over to the other node, so only one is active at a time. From the perspective of the DHCP, I have a much easier solution. I can simply provision several DHCP servers, because usually you might have the idea that it's a bad idea to run several DHCP servers in a network, because it's a pure black magic how clients are deciding whether the first or the second offer is to be used. But actually, if I'm provisioning or if I'm offering the same thing, then it's okay for me to run dozens of DHCP servers. So that's what happens here. So I simply spawn up a new namespace on another network node, which is serving the same information to the clients, and that's how it can be working. And yeah, and don't forget about the DVR option. So many vendors or many companies having a problem with the network node concept, that we need to have a lot of network nodes in order to provide the necessary bandwidth for all of my let's say VMs, because most of the VM traffic is practically a node sort traffic. So we are communicating to the internet, and towards we have a traffic to the VM, and also we have a problem with the intertenant or let's say east-west traffic that is coming from one compute node to another, but going between different tenant networks, that this has to pass through the network node as well. So in the worst case scenario, I need to have as many network nodes, as many compute nodes I have, and this is something I don't really want. So we're somewhat stepping back to the original idea what we had in the Nova network previously, that all the compute nodes are having a direct connection to the public network, and we say that the routers over here are just implemented by the compute node itself, so we don't have a separate network node just to provide floating IPs, for example, for the VM. So everywhere we have a cool router namespace, that guy is talking to another cool router namespace on another compute node to do this kind of east-west traffic. And when there is a VM over there who is needing a floating IP, then I'm setting up a FIP namespace in order to provide that extra functionality. But this is happening on a compute node. So from the AG perspective, the thing is that now we can practically, in case you have an error, in case you have a crash of a compute node, then you simply evacuate the VMs, and the other compute node will set up the same router namespace, FIP namespace, and all the IPs required there in order to provide connectivity for the VM. So that's a solution. The only missing piece, what we were missing till the Mitaka release, was another kind of functionality that was still served by the network node, and that was the so-called SNAT kind of namespace. So if your VM has an IP, I mean have a floating IP, obviously there's a way it can communicate with the internet. But what if he doesn't have? He still needs to be capable of downloading a package or something like that, and that's what we provided by this SNAT. So in case you were flagging a router like an AG router, it couldn't be flagged as a distributed router as well, so it was either or. Since the Mitaka release, when you can have both, so which means that in case you set up something like a distributed plus AJ router, then the routers, I mean the cool router namespaces are behaving like the same, like in a distributed setup, but the SNAT namespace is going to behave like the original AJ routers, so they have keep alive and they communicate with each other and they fail over from one network node to another. So that's a complete solution for your DVR. And this kind of a patch is available since the Mitaka release. Okay, so we have 4 minutes left, if this is true over here. So what are the takeaways? The plain only OpenStack doesn't really give you a full-fledged solution for your paths. So the thing what you have is available through that link is this live with watchdog kind of setting. Of course, we have a fencing proposal, but not a complete and not accepted and not implemented yet. And you can check the vendor solutions like the one you have for Red Hat or others that will use you pacemaker remote and different kind of fencing agents and different kind of evacuation, let's say, resources in order to provide a kind of a failover of a VM from one to another. For Neutron, yeah, I forgot to mention at the point of Neutron, the Neutron is still having a kind of a bunch of bugs depending on the version which you are using about deadlocks. That's the way how Galera is giving you a notice about something like a concurrent change of a record. So when the write set merging has a failure, and that has to, it's not a problem that could occur, but I have to handle that correctly from the code. And release by release, we have one point in the Neutron code that is just generating this kind of error that has a result of something like a failed resource. So something like a router that is deleted, but the port of the router is not deleted. And if you want to delete the port, it will try about that the port alone cannot really be really deleted. You have to delete the port through deleting the router. And that's the point when you just pick up a MySQL terminal and fix that port by hand, and that's an ugly part of the story. So the best practice is running Neutron for Neutron. You have to run the Galera load balancer in a active standby way. So you should use only one MySQL node at a time, and in case you have a problem, you have to fail over to the other one. For all the other services, that issue is already solved, so you can run active. The Galera can be used active in those cases. Yeah, and for DVR, you can see the link of the specification for this kind of extra patch for setting up distributed plus AJ, and also talking about load balancers. That's also another kind of note you can have here, is that with the Octavia project, which is something like the default since the Liberty, you can have an active passive load balancer because we don't have namespaces, but rather we have VMs over here, and we can implement whatever kind of amphora we want. And the default behavior is that we can have, let's say, highly available load balancer as well there. And the Cinder is, you can see those kind of two specifications which are accepted for the Newton release, and we hope finally in the Newton release we can say that even the Cinder volume can be running now in a normal way. Okay, this is the end of the story, and please take your questions if you have any. 45 seconds left. So hurry up. Okay, so if no questions, thanks for your time. You can reach me all the time.